Good morning or good afternoon, everyone. I would like to welcome you all for today's webinar, Cycle-Accurate Semiconductor System Modeling with VisualSim. My name is Ranjit, Application Engineer with Mirabilis Design. The reason for taking up this topic for today's webinar is to look at the importance of a cycle-accurate level system design, and also trying to look at how one can create very accurate and efficient cycle-accurate models using VisualSim Architect itself. The session is going to be a combination of both presentation and demonstration. I'll be walking you through some demo examples, and also I'll be constructing a simple model to help you to follow the modeling process itself. Before getting started with today's webinar, I would like to go over a few logistics details. You can see a control panel, something like this, on your Windows right-hand side. And there is a chat window. Please post in your questions in the chat window. We have people in standby. And also, I'll be answering all those questions during Q&A session as well. So here's a quick outline to today's webinar. As you know, that modeling and simulation is present in the system design process from decades now. And also at the same time, there are different level of modeling abstractions that addresses specific challenges during the system design process as well. So we are going to look at different modeling abstractions that are possible in VisualSim Architect that plays a very crucial role in early design explorations. For example, trying to understand what is the power consumption of my proposed system architecture. How can I reduce the power consumption? What would be the right power gating algorithm? Or it would be a selection of a processor or a bus or memory subsystems and things like that. I'm going to walk you through some of the demo examples in which we're going to look at cycle-accurate level libraries for these different blocks and to be able to understand or generate different type of reports and analysis and to make design decisions. For example, selecting the resource clock speeds, or it could be designing a memory subsystem or optimizing your memory subsystem to achieve better performance versus power trade-off scenarios. Okay, so for those of you who has not heard about Mirabilis Design, we are Sunnyvale, California-based systems engineering company, and we have representations all over the world, like in US, China, India, Japan, and Europe. And our major area of focus is towards entirely into digital electronic space, all the way from aerospace to defense or automotive to computing systems or networking and semiconductor systems. The major product is called VisualSim, which is a modeling and simulation environment. I'm going to utilize this particular tool to develop the cycle-accurate level models and to run varieties of simulations or use cases to be able to understand the performance of the proposed system architecture versus the set of use cases or workload scenarios. About VisualSim Architect, as I mentioned, it is a graphical and it is a modeling and simulation platform. To reduce the effort that you might be investing on creating the model, we are actually keeping the modeling environment as a completely graphical and hierarchical, which means you're actually spending very little amount of information on constructing the models, but you'll be spending a lot of time on analyzing the system, maybe giving a different set of use cases, or maybe changing the configurations of the platform, or trying to run as many as test cases over the proposed system architecture to identify all the possible bottlenecks or the kind of challenges that you may come across later in the design process. The entire analysis, the kind of explorations are actually uh, around performance analysis and power analysis and hardware software partitioning and selection of the hardware architectural platform itself. So to be able to construct those simulation models, we actually provide a large set of libraries, which includes stochastic and cyclic rate level library blocks. Based on the requirements and based on the kind of problems that you may have, or based on the level of information that you have, you can actually select the right library blocks as well. And one of the very interesting point over here is almost every library block is embedded with timing and power information, which means you don't really have to construct two different models to conduct performance versus power trade-off analysis, but instead you can actually capture both timing and power information in a single model. And these library blocks are actually used to assemble your hardware architecture, software behavior flow, and network components and traffic scenarios, and generation of the reports itself, whether it is the latency graphs or throughput or utilizations or maybe some other fault tree analysis reports that you want to capture. All these reports can be actually generated out of the pre-built or pre-configured library blocks as well. And also we provide over 15 plus interfaces and algorithm libraries, which actually enables you to bring in the models that you might have constructed in C, C++, or Java, or MATLAB and Simulink directly into VisualSim environment and start exploring as early as possible in the design process. Okay. So if you come across any questions, please post in your questions in the chat window. I will actually look at these questions in between, and also I'll be looking at these questions in the end of the presentation as well. So looking at the modeling abstraction, specifically with VisualSim, we actually provide three different levels of modeling abstraction. We call it a statistical level of modeling, which is more of a delay-based modeling with abstract functional details. And this actually allows you to kind of gather or gain better understanding of the complete system architecture. It could be a complete complete system like a data center, or it could be an avionics system, or it could be a complete high-performance processing computing system itself, and things like that. You can actually capture your complete system architecture within few hours of modeling effort. And also the kind of analysis or the kind of reports that actually provides you will help you to make some of the decisions, such as how many number of resources that I need to have, or how do I distribute my tasks between multiple processor cores, or it actually allows you to understand feasibility of the project itself. So we call it as a first level of system sizing in which you have very little amount of information, but you want to actually try to explore or try to gather more and more information, maybe from the customer, or maybe from the management, or maybe some other team located somewhere else. So you actually start building the models using statistical level library blocks. And the other approach in this webinar I have combined together are hardware level modeling and cyclic rate level modeling. So if we are actually looking at the level of SoC or a network on chip or things like that, we would actually combine these two abstractions together. The reason is we actually provide the modeling IP library blocks for hardware blocks. And also all these libraries are cyclic rate, which means these two levels are exactly the same in our case there. But if you're looking at a complete end-to-end system, or maybe when you're looking at multiple subsystems and things like that, you can actually keep some of the portions as a statistical, and some of the portions as hardware level, in which you might be using abstract hardware library blocks. For example, it could be a DRAM or a cache and things like that. I'm going to show you those library blocks. And some of the portions you may actually go into a very detailed level, or maybe very granular level of details you may actually go into it. For example, you might want to consider a very detailed DDR memory and a memory controller. And you want to understand what happens if I go with how many memory banks that I need to utilize, or what happens if I select a certain configurations of memory access times, or it could be what happens if if the memory is being used with uh, sequential versus random read or write operations. So these are the kind of questions that you may actually have. And one thing that we have to consider or we have to keep in mind is once you actually go into a level of hardware level modeling or cyclic rate level modeling, so it is something like you have already identified a particular architecture, but you want to kind of explore more on that architecture. For example, maybe changing the configuration, maybe changing some parameters, such as the clock speeds, or maybe changing the process pipeline stages, or it could be the size of the cache memory, or things like that. Those are the kind of parameters that you may actually change, but you may not really change the complete architecture as you would do in the case of statistical level of modeling approach. At this point, I would like to kind of give you a quick view of a simulation model to try to understand how a simulation model can be. I'm going to show you exactly the same model in two different approaches, one with statistical level and the other one is with hardware level of modeling approach. So the model that I'm going to show you is a dual processor system model. And in this case, what we have here is this is a statistical level of modeling in which I have my CPUs defined as a very higher abstraction level. So I don't really have enough information about how many pipelines I have or the caches or size of the cache defined or how many number of execution units I have. None of those informations are embedded or provided in this particular processor model. Whereas we have this bus arbiter and cache and RAM blocks, these are pretty much detail level over here. Uh, these cache and DRAMs are not really a cycle accurate, but these are a kind of hardware accurate library blocks with abstract details, I would say. For example, if you look at this RAM block over here, this actually provides you some of the parameters, such as you can define the access times for read activity, write, or prefetch, and things like that. Also, you can provide the buffer sizes and the size of the memory itself, the rate at which you're running, and also you can define what is that memory type that you're selecting. For example, it supports all the way from SDR to DDR3, QDR, and RAM bus. You can actually dynamically select these and run the model. Similarly, cache memory as well. Sorry, cache here you have, you can define the hit expression. So in this case, we are considering my external cache is actually having a hit rate of about 84%. So this is a kind of assumption based on the size of my memory and the rate at which I'm running this particular resource itself. Whereas this particular bus arbiter, what I have over here, we call it as a custom or proprietary bus generator. So which actually helps you to kind of generate pretty much every bus technologies that are available in the market. And also we have a standard uh, bus technologies such as AMBA bus or AXI, PCI or PowerPC buses and things like that as well. Whereas in addition to that, if you have any proprietary bus technologies, you can use it here. So coming back to our statistical level modeling versus cycle accurate level modeling. So in this case, what I have over here is at the bottom, I have defined my workload and use cases and mapping to my hardware architecture over here. So the traffic block over here, it actually helps me to generate traffic at certain interval. It could be for every 1 millisecond or 10 milliseconds, or I could wait for a particular event to occur, and once a particular event occurred, I can generate traffic. So in this expression list block, I have defined all the different cases. For example, I'm trying to understand in which processor I'm going to execute or and how many number of bytes I'm actually sending it over and things like that. If I look at this particular mapper block, this actually helps me to map to one of these two CPU blocks. We call it as system resources. So if there is any kind of hit or miss conditions, it actually go to the cache or DRAM and get the data and starts running. So if I go ahead and run the model for this particular architecture, the kind of reports that I'm actually generating includes end-to-end latency. Oops. Uh, uh, I can see that my voice is breaking. I'm not sure if you can hear me clearly.
It looks okay now. It was breaking a few minutes back.
Okay, that's great. Thanks. So the kind of reports that we are looking at over here includes end-to-end latency. And also I'm looking at the activity of my processor or my resource itself. So in this case, I'm looking at when my CPU1 is active, how long it took to complete a particular task and things like that. But more interestingly, what I'm looking at over here is I'm looking at utilization of my resources. So let me stop this and maybe increase the. So I'm not going to run this. Okay. So what I'm looking at over here is the configuration for the given configuration. What I'm looking at here is number of transactions entered is about 26, which means my CPU1 actually received 21 tasks, and each task is actually having a total delay of about 6 microseconds. And my utilization is way less over here because I'm not running too many tasks over here. Also, if I look at the other details, such as um, so what is the utilization of my other processor and things like that, these actually provides me a kind of idea about which processor is being used most and which one used less. So that actually gives you an understanding about how do I distribute my tasks between those resources. So if I actually look at the exact same system with um, a cyclic rate level model. So in this case, if you look at over here, the bottom sequence is quite similar, or quite the same. There is hardly a couple of blocks that we have added. But if you actually look at the hardware architecture, we have actually replaced a statistical system resource block with a detailed processor model. So if I double click on this processor model, here we have a list of parameters that actually helps me to configure my processor. In this case, we are actually saying I have two cache execution units, and I'm actually running at a particular clock speed, which is actually defined as a top-level parameter, which is about 1 gigahertz I'm running at. And also, I have a standard 4-stage pipeline defined over here. And the processor is of 32-bit wide. And all of the parameters such as the blocks, L2, cache, and DRAM are exactly the same. I don't have any additional details. And in addition to looking at the behavior flow, I have my workload generator, and also I have an additional block called task generator over here. So what it does is it is actually generating a synthetic instruction for my processor, which I have defined over here. So you may actually receive a image rotate algorithm. The task generator will actually generate a synthetic instruction for that particular task, and that will be actually sent over to the processor block using this dynamic mapper. So you may actually ask me a question like how these blocks are connected. So we actually call it as named mapping. So if I double click on this dynamic mapper, it is actually referring to my processor block, which I have over here. So by calling the name, we actually these two blocks are directly connected. Similarly, my dynamic mapper 2 is connected to my processor 2 at the bottom, which you can see over here. And once the processing is over, we are actually just trying to capture what is my end-to-end latency or what is my MIPS that I have captured. So I'm going to run the model with same configuration. The kind of reports that I'm looking at over here includes what is my MIPS and what is my latency. So the latency that I'm capturing over here, the red one tells me the latency across my first processor, while the blue one tells me latency across my second processor. But if you look at over here in this particular model, what we are looking at here is not just trying to understand the time a processor takes to execute it, but instead we are also considering the total time it takes to get the data or instruction from the external memory itself. So because that is where most of the designs are having the problem. So you need to actually, you must be able to capture the memory access timing information as early as possible. That way you can actually optimize or you can modify your memory subsystem or other way how you're calling your, uh, uh, or you can actually up or kind of uh, upgrade your memory management units and things like that as well. If I look at over here, my MIPS that I have captured over here shows me the red one is is the MIPS for my processor 1, while the blue one is for processor 2. So in this case, I'm actually looking at an MIPS of about 770 MIPS when I'm actually running my processors at 1 gigahertz. So I need to talk more about the task generator. I'm going to come back to this particular topic in a little while. Okay, so if you have any questions, please go ahead and post in your questions in the chat window. I'm going to give a little while. Okay, so I just showed you an example around a statistical level of modeling versus hardware architectural level modeling. So the main difference between these two architectures that you just saw was you need to have more information about a particular architecture, and you are actually trying to explore a particular configuration or maybe a sequence. In that case, you may actually have to go with a cycle accurate level modeling approach. If you have a very little amount of information and you want to or you want to capture your design as quickly as possible, in that case, you can actually go with a statistical level of modeling approach. Okay, so why cycle accurate level modeling? As you know that cycle accurate level modeling, it actually helps you to kind of capture details about your architecture. It actually helps you to verify your architecture with different sort of use cases. And also it helps you to kind of conduct performance analysis or architecture explorations, and power estimations and management. And also it actually helps you to kind of understand or analyze interactions between your processors, memory, cache, and memory management units as well. And also one of the biggest advantage that you're going to get out of these cycle rate level modeling with VisualSim is you'll be getting over 95% accurate performance and power values even before having your RTL ready. It could be if you are going to write any cycle accurate level models in C or C++, it definitely takes more than 6 months or nearly 1 year of effort to build a particular architecture. But with VisualSim, you will be actually constructing these models very quickly in a matter of weeks to months based on the complexity of your system platform itself. The whole idea here is that you will be actually spending very little amount of information, time on constructing your models while you're spending too much time or maybe more time on analyzing your architecture to make sure all the corner cases and all the different scenarios are being evaluated thoroughly. Okay, and these models can actually helps RTL design teams and software development teams to make some changes into it, and they can actually keep these models as a kind of golden reference files to make sure the entire design process is in sync with what was planned earlier. Okay, and looking at the modeling of hardware blocks, we actually provide, as I mentioned, parameterized IP library blocks. And also we provide generators for rapid constructions of custom components as well, be it a processor, be it a bus technology, or maybe some other accelerators and things like that. Using library generators, you can actually create custom components very quickly as well. And also, as you have noticed in my previous model, you can actually have a multi-clock domain as well. For example, in my case, processor is running at 1 gigahertz, whereas bus is running at 800 and DRAM is running at 650 megahertz. You can actually have a multi-clock domain as well. Here's a quick view to our library blocks. We keep on adding additional libraries, almost one in every month. And also we, based on customer requirements, we construct those library blocks and validate it and ship it to our customers as well. So if you look at the libraries, these are not specific to a particular domain, whereas this covers all the way from avionics to semiconductors and networking and embedded platforms, FPGAs and things like that as well. Okay, so okay, for constructing an hardware architecture, we provide the library blocks, which you can actually quickly configure it based on your requirements. So how about defining a software behavior? So we actually provide mainly two types of ways to bring in software behavior or define the software behavior. One thing is you can bring in or you can import application address or statistical trace from your real hardware or maybe the compilers. And you can actually generate, the other option is you can generate synthetic instruction sequence using VisualSim task generator. So the image that you're looking at over here is a sample snippet of a instruction mix table that we actually use it along with task generator. In this case, what you are seeing over here is mainly two different columns. One thing is the first portion, which actually talks about the integer and floating point. And here you'll be listing out all the different type of instructions that are available or that are there for your processor. And also you'll be listing out the mnemonics list over here concerning or corresponding to those uh, mnemonic types. And then you'll be listing out all the tasks that are there in your system platform. For example, in this case, I've given a dummy name called my task one and have considered this particular task is going to take about 200 instructions. And out of 200 instructions, 80% will be integer type and 20% will be of floating point. So coming to this particular number of 200 instructions, this is quite simple. It will be based on how many number of lines of C or C++ code that you have, and you can multiply with some 5 or 6. The amount of number that you are coming with will be actually kind of sufficient enough to have this number as well. But if you have any kind of statistical trace of it, for example, the list of mnemonics or things like that, those can be actually directly imported and that can be directly used along with VisualSim Architect. So using, or I'm going to show you an example over here. So in the previous example, I showed you a block called task generator. So this block actually reads a file called instruction mix table. And I'm going to open up that particular file to show you how that file would look like, and variations to that particular file would impact performance of the system. In this case, I just open up my file, and what I have done over here is I have considered integer type of about 100%. I'm going to make it as 50% of integer and 50% of floating point instructions over here. Okay, so what it means is out of 2,000 instructions, 1,000 instructions will be of integer type, while another 1,000 instructions will be of floating point instruction. I'm going to save this block, and I'm going to run the model, trying to understand what is the impact of changing the instruction sequence on the performance. Earlier, we actually seen a maximum MIPS of about 770, whereas now you can actually see here it has actually dropped down to 220 million instructions per second. There's a kind of huge degradation in the processor performance because I'm running a lot of floating point instructions. So you may actually have a dedicated floating point execution unit so that you will actually uh, you can meet your performance requirements in that case. And also earlier case, we were actually looking at a latency of close to 5 microseconds or something like that. But now I can see here my maximum latency is of about 9.4 microseconds. So this is kind of gives you a understanding about how these numbers or how these plots can actually help you to make decisions on the platform. So this actually tells me that how do I need to have a dedicated floating point engine, or how do I schedule those tasks between multiple processing units? And also we have additional reports such as I'm looking at statistics of my complete platform. For example, in this case, we are looking at instruction cache hit ratio, which is actually having a mean hit ratio of about 85%. And also, we are looking at processor task delay as well. In this case, you can see here, maximum delay is of about 9.3 microseconds, whereas mean task delay is of about 4 microseconds. Okay, and in addition to that, you have additional details such as what is the throughput, or how much a particular cache is utilized by a particular processor. And you can actually make or utilize these reports to make additional design decisions as well. Looking at this particular timing diagram, this actually helps you to kind of debug and try to understand if all the instructions or all the resources are actually working perfectly fine. Uh, you may actually have a lot of dependencies between those, and this actually helps you to track down those activities as well. So you don't really have to read those timing diagrams. You can actually enter in some of the kind of breakpoints, and you can start debugging your models as well. Okay. So as I mentioned earlier, please post in your questions. We have people in standby. They'll be answering all your questions. And in addition to that, looking at performance alone is not sufficient. So as you may know, nearly about 60% or at least 50% of power optimizations can be actually achieved only at the early design phase. And about 10% of optimizations can be actually done later in the implementation phase, maybe the RTL level or maybe at gate level translations. So that actually translates that you need to make sure that you are actually considering all the different possibilities of reducing power consumption of the platform without compromising your performance itself. To enable that, we actually provide a complete comprehensive solution, which actually includes power generation, storage, consumption, and management. So with regards to power generation, we actually provide power harvester or energy harvesters. And with regards to storage, we actually provide different sort of battery library blocks as well, all the way from lithium ion to nickel cadmium and things like that. And consumption is based on a dynamic state change activity of a particular component. And also it can be, you can actually force a particular component to go from one power state to another power state when you are actually implementing your power gating algorithms. Okay, and the kind of uh, inputs or the kind of configurations that you would be doing includes the state change informations or transition details, and you may actually consider entering power consumption details for each component at different power states. Also, you can include the frequency and the voltage details and things like that as well. Okay. And at this point, I would like to show you a quick demo example to understand how we can actually introduce power gating algorithms or additional logic to reduce the power consumption. I'm going to open up a model, In this case, what we have here is a multimedia system platform with an ARM subsystem and a memory subsystem on the other side, and we have an AXI bus, and at the bottom we have defined the applications. For example, in this case, we have uh, image processing platform. Here it is. And the task is you have an image sensor, and then you have your read frame, decode frame, video post-processing, rendering, format, and rotate. And these are actually can be run on the subsystem, considering your system as a software piece of platform, or you can select a particular task and run on a different core. For example, in this case, we are looking at, or we are running rotate frame algorithm on a hardware accelerator. Okay, so we have a power table on the left-hand side here. The power table would actually look something like this. So what it includes is it includes all the different components that are there in the model. For example, processors, memories, buses, and peripheral devices and things like that. And also you will be providing uh, the power values. For example, what is the power consumption in active state, standby state, wait state, and if you have any other additional states, you can list out those additional states as well. Okay, I'm going to come to the other blocks in a little while. So what I'm going to do at this point is, in this model, we are actually expecting about 13,000 macro blocks being processed, and power consumption should be under 1 watt of power. So that is a kind of high level requirement that we are having. And looking at the macro blocks processing, we were expecting about 13,000, but here we are actually getting about 14,000 macro blocks are being processed. So which means performance-wise, my platform is working perfectly fine or really good. But if I look at the power consumption, my average power consumption, it is actually quite strange here, or I would say quite dangerous here. I was expecting power consumption should be under 1 watt, but it is actually going close to 1.5 watts of power. And looking at the different device power consumption, I can see here my hardware engine is consuming more than 35% of total power consumption. And also looking at the activity of the hardware engine, I can see here it is in always on state. So whether you have tasks running on your platform or you have nothing, it is in on state all the time. And that is actually the major reason for increased power consumption. So what I'm going to do at this point is I'm going to actually move or shut down the hardware engine uh, if I'm actually not running any tasks for a period of time. For example, I'll be waiting for 1 nanosecond or 1 microsecond of time period. And if I don't receive any task request, I'll actually shut down to a standby state or deep sleep mode. Okay, so I'm going to add that particular line here. I just double click on or open up the configuration for the power table. I'm going to define that over here. I'm going to call this as if my standby state, or I would say if I'm actually in standby state for about 1 nanosecond, I'll actually push this device to a maybe idle state and try to understand what is the power consumption. Okay, I'm going to commit and run the model again, try to understand what is the impact of it. If you see here, it is actually active for a very short time period, and it is actually pushed over to an idle state, which is actually having a power of about 10 milliwatt of power. And looking at the performance-wise, number of macro blocks is still looks good, close to 1400, whereas power consumption over here, it actually looks very good. We were actually expecting power consumption of about under 1 watt of power, and we can see that. And also, if I look at the power percentage of different devices, earlier case, my hardware engine was consuming more than 35%, whereas it is now close to 1% of my entire system power consumption. So if you actually think about it, if you have identified this particular problem later in the design process, so it would be a kind of really a mess, and you will actually have to kind of completely, you may actually completely come back and change the architecture or make necessary decisions to be able to meet your power requirements. But with this approach, you're actually identifying all the possible error scenarios, the kind of bottlenecks upfront, and validating the system platform to make sure uh, the platform is meeting all your requirements, either in terms of performance or power and things like that. So the kind of types of analysis and explorations you can consider as you can do a variations in the task arrival rates. What happens if instead of receiving a task request every 1 microsecond, what happens if I'm receiving that 10 nanoseconds? Whether my processor is going to handle that much traffic or not. Do I need to actually increase my buffer to be able to sustain all the tasks? And you can change the data sizes, and you can experiment with random read or versus sequential read and things like that. And also you can experiment with ordering of the tasks in the use cases as well. So how a different set of tasks are being actually executed on the platform, and what is going to be the impact of it on the complete system platform. And it could, in addition to that, you can consider doing variations in the priorities or generating some interrupt messages quite often and trying to understand impact of it on the total system performance. On the hardware configurations, you can actually change a whole varieties of things, all the way from changing the component. You can change the clock speeds or certain set of parameters such as clock speed or memory technology that you're selecting or size of the memory or execution units in a processor and things like that. So I would like to go over a particular model at this particular point. So the model that you're looking at is a dual channel DDR memory platform. In this case, we have a very detailed cyclic level memory subsystem with an ARM by AXI bus, while on the left-hand side, my master or the processors are actually completely abstracted out. And here we are actually just considering as the requests are coming at a particular rate. And these can be a sequential read, or these can be a random read or write operations. Okay. Also, these traffic generators actually allows me to change the rate at which the requests are coming in as well. And also here I have a certain set of parameters as well. For example, I'm looking at how many banks I have, or how many, or what is the rate at which I'm running my memory, and width bytes and command buffer length and things like that. And if I double click on this memory controller block, what you see over here is a whole varieties of different parameters, all the way from what are the different type of DRAM types that you need to consider. In this case, it is a LPDDR3 memory, but instead, or in addition to that, you can consider a different set of memory technologies as well. And you can define your memory access times. It could be your cache timings or RCD or TRP or TRAS and things like that. Also, you can consider defining extra timing, for example, DQSs or uh, TRRD and things like that as well. So one of the interesting factor that we provide over here is you don't really have to manually configure all these parameters. So we actually have, provide a capability to read all these different parameters from a file, and the block itself will actually configure itself by reading that those details. So what I'm going to do is I'm going to open up the file called memory standards. So what I have over here is, in this case, the model was actually used to experiment with different type of memory technologies. In this case, we were actually using micron memory technology, all the way from 933 to 400, 450, 500, and 600 clock speeds. And we have the timing information associated with different technologies as well. So you can list out all these in a text file, something like this, and you can run through the or change the memory types and run the model and trying to understand which technology is actually providing you a better performance versus power trade-off. So I'm going to run the model. In this case, what we are looking at here is we are looking at instantaneous versus average power consumption. So what you see here, the blue dots are instantaneous power consumption when your memory banks are being utilized, while the red one is the average power consumption. So this actually tells you that average power consumption is very less, while the instantaneous power consumption can see a lot of peaks here. And these peaks actually could be very interesting or really required to make your decisions on the uh, heat sink, or it could be the kind of cooling costs that you may actually have to consider. And those kind of decisions can be actually conducted. And looking at this particular timing diagram, this actually tells me the memory signals. For example, we are looking at the activities across different memory banks and active or pre-charge signal arrivals and things like that as well. Okay. And in addition to that, we're generating some additional statistics as well, looking at what is my throughput or what is my uh, number of IOPs or things like that as well, or the total delay across that particular memory technology. And these kind of reports will actually help you to make decisions on if you have selected a particular right memory, or you may have to consider changing the memory technology uh, or the way how you are accessing the memory itself. Okay, so in this case, these two are the ARMBA AXI memory controller and memory blocks are very detailed with hardware accurate level details. And we have actually seen the power consumption reports close to 99.5 accurate against the JEDEC standards itself. Okay. So looking at the other reports that are being generated automatically from the tool, that includes end-to-end latency and task delay. And also we generate the reports such as throughput and utilizations and task delay across the resource. And all these different reports are provided in minimum, maximum, mean, and standard deviation, which may actually help you to make the right decisions. With regards to a processor, we actually provide statistics for the internal cache and registers and execution units and pipeline activities. And also we provide details on how much time the processor is installed and what is the flash time and how many times thread swaps are occurred and the context switching times and things like that as well. And you can generate custom reports if you're looking or looking for those as well. Okay. So to summarize this particular webinar, uh, the major reason for considering cyclic grade level modeling with VisualSim, it actually helps you to kind of explore lower level of details of a system platform with a very little amount of effort on constructing the model, while you can spend more and more time on analyzing to make sure your non-functional requirements, be it performance or power or maybe utilizations and things like that, meets your requirements. And also uh, trying to validate the correctness of the system platform with different use cases and test cases and different sort of architecture configurations and things like that. And also, these models are actually constructed within a few months to or few weeks, which actually tells you that you're spending very little amount of time. And the model can actually play as a communication document or a kind of golden reference file that actually helps to communicate between the RTL development team and software development teams to make sure what are the kind of considerations that must be considered and things like that. And the models can be actually exported into a HTML page along with all the documentations of the tool, of the model, and it can be actually shared across internet, and someone who wants to understand or who wants to explore the model can actually just open up a browser and use the link what you're going to give, and try to explore the model and try to see if the requirements are meeting what it is being defined. Okay, so this concludes this webinar, and now the session is open for questions and answers. Please post your questions in the chat window. I can see most of the questions are being answered, and I can take up any additional questions that you may want to get answered. Okay, so in this case, what I'm going to do is I'm going to actually construct a model. To do that, what I need over here is I'm going to need a digital simulator, which actually includes, I'm going to define how long I need to run the model. I need to have a processor block, and I need to have a instruction set. I need to have a cache. I need to have a DRAM. I need to have a bus arbiter and bus interface. Just connect these together. I'm going to make connections to the processor block. I'm going to connect these bus interface to the cache, and I'm going to connect this to a DRAM. Okay, so this assembles up my processor. So what I need to do at this point is, sorry, processor and my memory and the bus and things like that. So what I'm going to do at this point is I'm going to configure my processor for a simple design. So what I'm going to do is I'm going to consider running my processor at 1 gigahertz, and I'm going to consider the cache execution as units as 3 units. Whereas integer, I'm going to consider only a single integer unit, and I'm not going to consider any floating point. I just made those changes. I'm going to consider an external cache as well. I'm going to call this as cache 1, which actually goes to my cache on the other side. So if there is a L2 miss, it actually goes to my cache 1 and tries to get the data. I'm going to run this at the same clock. I'm going to call this as int. I'm going to commit it. And in the instruction set, what I'm going to do is I'm going to bring in, or I'm going to delete all the additional details because I'm considering a very simple scenario. I'm going to call this as int1 or IU. And you don't really have to define all this in case if you're not designing any proprietary processor models. For all the standard processor block, we actually provide all these pre-configured, so you don't really have to worry about it. Okay, just named it as custom processor. I'm going to name that or use that name in the processor instruction set parameter over here. Okay, so I'm going to commit it. So what I have here is I have actually configured my processor to run these 4 instructions. That includes IU add, IU shift, rotate, and logical. Okay. So what I need right now is I need to model the workload scenarios. I am going to bring in a traffic block. I'm going to call this as processor DS. The reason for using processor DS is we actually, all the models communicate using a file called data structure file, which you can correlate with a struct in your C, which will actually have multiple data types with a predefined values in it. So we actually send a complete data structure from one block to another to make the decisions or to make computations and things like that. I'm going to generate the traffic at every 1 millisecond. And in addition to that, I'm going to configure some of the parameters such as where I'm actually going to run. So we call it as regex expressions. So which means I'm going to define some or update some of the fields such as what is my destination. So it is a destination is equal to processor 1 because this is the name of my processor in my model. And I'm going to define a hop, which is again a processor 1. So now the very interesting point or part of it includes a instruction. So what are the different type of instructions that I'm going to run? Okay, so I'm going to name those instructions as these. IU add, okay, IU shift. So it is possible to get these instruction sequence for the applications that you may have with you. If you have these instruction sequence, you can actually maybe in Excel spreadsheet or something like that, we can actually read those spreadsheet information and generate a instruction sequence that can be actually utilized with the processor block. Okay, so I'm going to commit this. What I'm going to do at this point is I'm going to actually directly connect this block over to the processor over here, which means I'm actually going to send these tasks over to the instruction in or to the processor. There are multiple ways to do it, and this is one way of connecting these blocks. I can do it without or using a mapper block as well, as you might have seen in my previous model. So what I'm going to do is I'm going to just check if all the parameters are correct. This is called SDRAM. And if there is a cache 1 miss, I'm actually going to go into this particular memory and get the data. And it looks good for now. I'm going to run the model and trying to see what is the error that I'm going to get. So what it tells me is I have a duplicate name. So this is a very good report, which means these bus interfaces are actually having the same name. So I need to update this to a unique name. Okay, I'm going to run the model and trying to see what is that I'm going to get. So what I see over here is I'm actually getting only one transaction out. So this means there is something wrong in my model and I need to debug it. So there are multiple ways that we provide. One thing is you can try to understand if the requests are coming in to the processor, and you can see here, or you can double click and check if everything is defined correctly. For example, your L2 cache or L1 cache and all those miss details and all that. It tells me cache 1. Okay, so this looks good. I'm gonna go again here and trying to see if this looks good. Memory type as well. And I'm gonna just double check the processor name. I'm gonna look at if I'm actually getting any transaction out of my reject code. So which means if you have a queue overflow or a buffer overflow in your processor, or if the processor is not able to process the transactions, then you will be actually having a overflow there. Okay, so I'm gonna looking at the reject port. What I can see here is the problem is really the instruction queue is full. So there is not really any kind of activities that we can see. I'm gonna go back and try to see what is the real problem. Okay, so I'm gonna run this at the same speed at which I'm actually running, or maybe close to 800 megahertz. And I'm gonna run this at 800 megahertz, and this at 850. I just change this to DDR type. INT. I'm gonna run the model. Okay, so it is actually trying to utilize a default routing table, which actually possibly giving me the error. I'm gonna run the model. So what I can see over here is I am able to run the model. So what you see over here is I'm actually getting an MIPS of about 36 MIPS here, and number of cycles in the processor is about 108, including the context switching cycles and all that. And cycles per instruction is about 27. So at this point, what I'm going to do is I'm going to make a very interesting point. Here, in this case, by default, I used only 4 instructions. So what I'm going to do is I'm going to use the same 4 instruction multiple times. I'm going to just copy and paste it maybe hundreds of times. I'm going to commit, and I'm going to run the model. So what you see here is I actually increased the number of instructions now. So what you see here is cycles in processor is actually 734 now, whereas cycles per instruction actually reduced. And also MIPS actually increased considerably here. Earlier I was getting only about 36 with just 4 instructions. And now I can see a total of about 842 instructions for my for the task that I'm running. So this could be actually one of the value or the kind of report that you may actually be interested in looking at. Okay. So in terms of debugging skills, we actually provide a lot of it. For example, you can look at how exactly the processor pipeline works. I can look at it by listening to the processor or table, and you can look at how exactly the processor pipeline is actually being executed. So which instruction is considered and which one is active, and when your processor is installed, or maybe waiting for the data or instruction from the memory itself. Okay. So as you can see here, we have actually quickly assembled a system with a processor, a bus, and a memory subsystem within few minutes. So this could be a very simple example, but you can actually construct very complicated models within a matter of a couple of hours to days using these pre-built configurable library blocks.